Hi everybody, welcome to week 2 of our Python for Biologists class. As you recall, we are doing a 6-week session to teach some of the basics of Python. I'm showing on screen a flowchart that we talked about last week. I just want to kind of remind people what our eventual goal was for this 6-week session. So we have start points and end points shown in purple, we have decision points marked in blue, and we have processes marked in yellow. Last week, we created just a short script that we could launch within Python. We got Python on the path so that we could launch it very easily on our laptops. And that allowed us to run our code, which had hard-coded, as I said, the name of the software, the name of the database we wanted to read. But today we're going to make it a lot more flexible, allowing the user to provide the name of a FASTA sequence database when they call the script. And if they don't, the software will give usage information and so on. So we're using this as a way to teach the principles that underlie all programs in Python. The hope being that you understand what are the kinds of elements you need to include whenever you're doing any project. So, of course, don't forget to start with a visualization of all the steps. Try to put together a flow chart that marks the key pieces that are going to have to happen along the way, in what order. All right, now I believe I breezed by the inclusion of an import statement last week, but I wanted to remind people of what it's valuable for. There are a world of functions and library values that are available to you within Python. And a large number of them actually just ship with the language itself. So when you installed Python on your computer, you made the system module available to you. Oh, we have that's a short to speaker, okay. So one of the modules that we're going to explain today is sys, S-Y-S. So whenever you include sys, or import sys into a Python script, you're giving yourself access to all of the functions and variables that it makes available. Did I see a question for me? No question? Okay, cool. So I thought I would point out three things that end up being useful a lot of times that come along with sys. So we see that sys.version becomes available. This is a variable that's defined within the sys module called version, which is a string describing all the details about which version of Python someone is running when they're using your software. So if you had written some Python 3 specific commands as part of a script, and the user had only installed Python 2, you would be able to determine that here. So having the access to system version is useful. The one that we care about most today is sys.argv. Frequently, when people launch a piece of software on the command line, they don't just run that program itself, they also include an argument. So if you were sitting in a command prompt, you might say, for example, dir enter, and that would give you a directory listing. That's fairly straightforward. But you might instead say dir dot anything starting with a period first, and you can see that in my directory that's just a subset of all the files. So dir is the command, and .star is an argument given to that command. Does everyone see that? So you, having written a piece of Python software, frequently will need to be able to see what things did the user specify along with the name of this program to launch it. Okay, that is what argv is very good for. So we will be showing how to use that today as part of our target code. And then finally, I have given an example of sys.exit. So exit is a method here. Well, it's a function within the sys module that will force the Python interpreter to stop right where it is, with no possibility of continuing beyond that point. So we'll use both of those last two in the software. All right, now I definitely feel like we need to talk about the subject of iteration. Iteration. Now, that's a kind of formal term. Have people heard the term looping? Looping? Okay. Loops are used whenever we want to repeat actions. So if we flip back to our top diagram, you can see that I've actually written a loop right in here. Can we read the next line? If so, update statistics. And then can you read the next line? If so, update statistics. This is an example of a loop, something where we repeatedly interpret lines of sequence until it's not possible to read another line of the file. So that's an example of a loop, and loops tend to get implemented in two key ways. In the first way, you have a set number of times that you want to execute a certain type of code. That's a for loop. Most often, that comes about through a case where you want to do a certain action a fixed number of times. But very frequently in the world of Python, we end up working with a list of items. So I'd point out that in this first case, instead of saying color equals red, for example, we are specifying that colors is a whole list of colors. So you can see that it's red, then orange, then yellow, then green. It's one variable, but it equals that whole list of items. So I can then write a for loop that says this color is an item in colors. So this color will first be equal to red. This color will next be equal to orange. This color will then be equal to yellow. And this color will then be equal to green. And for each of those different values, it will execute this code. I think everyone remembers that from last week that print will take whatever it's passed as an argument and dump that out to the screen. But I've made a kind of more complex looking print line here. We start with this color. Now we've already said that this color is going to be each one of those colors in the list above it. That's pretty straightforward. But you can see that I've done some math here with other strings. So I've added to this color a space character. That's not two quotes directly next to each other. The double quotes are separated by a space. So we're saying we want to have this color followed by a space, followed by, and now we've got this gobbledygook down here. So what does that mean? This color is going to equal each of those strings in succession, but we're not going to print this color itself. Instead, we're going to ask, what is the length of this color? So what can that mean? These are strings, which means that they're a series of characters. The length function, len, is going to report how many letters are there in that color. So for red, len returns the number 3. For orange, len returns 6. For yellow, it returns 6. For green, it returns 5. And that's great. And you might think, great, why don't you just print that? What's all this other business? The trouble here is that we are combining together strings, such as this color, or such as the space character, and a number, which is the length of the thing that came back from the len function. So Python requires us to make them all the same type. So we need to force this number that came back from the length function to be treated as a string itself. So if you had the answer 15, if you'd given it some really absurdly long color name, then the number 15 popped back, you would need it to create a string containing a 1 and then a 5 to make the number 15 turn into a string of a 1 and a 5. That may not seem like something that's obviously intuitive, but this type of casting back and forth is something that we need to be able to do quite frequently in lots of programming languages. So if you were simply to give the print statement a string plus a number, you get an error. We can show that example very quickly. I'm just going to start the Python interpreter here in this window. So I can say print orange. No problem there. Can I say print 6? I can. But what happens if I say print orange plus 6? You see that? This is an example where we're trying to combine two things that can't be combined directly. So I'm going to repeat that last command by hitting the up arrow, and this time I'm going to surround 6 with the string function call. You see that? Now we've got orange 6. And if I want those to be separated by a space, I can add that part. So I don't mean to be pedantic about this, but I hope that explains why we've got all that extra verbiage in there. For after getting the length out, we need to convert it to a string. Okay, it is possible to use some functions to create ranges of numbers. So I'm introducing the range function here. I can say range 10, and I see that it returns a range object, which is a little odd. But here it is. It's going to give us 10 values, 0 through 9, to work with. Okay, so I actually have this code in one of the files that you downloaded today. So if you take a look at sets iteration Python code, it was one of the files that I added to the list yesterday. You should find somewhere in that code, range returns a series of numbers. I'm going to just grab this block of code and then run it right over here at the interpreter. Okay. So I first printed a label of what this section is doing, the first 10. I created range 10 and then told it to iterate through each member of range, and each time it was to print whatever number it was on within that range. And we see that 0 printed first. Remember, computer scientists from the cradle do not start by counting at 1, 2, 3, 4, 5. They always start at 0. And Python is one of these languages that starts at 0. So when you specify, I want a range of 10 numbers, the first one that comes out is always going to be 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, what happened there? It chopped off before it got to 10. So to supply a range of 10 is going to give you 10 values back. But because the first one is 0, the last one is 9, not 10. Odd but true. Okay, so there are a few things that are going to be a little challenging to keep on top of as we careen through this. You can also do some crazy things with range. So if instead of counting from 0 to 9, which is what range 10 equals, you might instead go from 4 to 20 in steps of 2. So range doesn't require that you hit every number between those two. That is also in the code that I provided on the side. So if I grab this code and run it over here, we can see that the first value, 4, is used as a starting point, and it counts by 2s because that third value specifies give me every other number. But it doesn't actually get to 20 because 20 is the first value that's outside that range. It's the too high criterion, essentially. So 4, 6, 8, 10, 12, 14, 16, 18, and then it stops. All right. So these for loops represent a way to iterate, to repeat a certain section of code for a fixed number of times, once for each in the set. But I want to point out that there are lots of odd places where these items to iterate through can come from. So I wanted to point out this odd example right here. So my word is equal to abacus. All right, we have just one string here. But this single string can also be regarded as a series of characters. Right? We look at that and we say, well, there's an A, and then there's a B, and then there's an A, and then there's a C, and then there's a U, and there's an S. So in the same way, the for loop can be used to decompose a string to characters. So in this case, we tell it to set up a variable that passes through each of the letters of that string and can print each one of those in series. So I have that code right here. I'm going to just grab that guy, come over here, and paste her in. Oop. Sorry, I missed it. Let's try that again. Do. Okay, there. And we see that this letter sequentially takes on the value of A, B, A, C, U, S. Each one of those gets printed separately. So although we may think of a string as being one thing, one word in this case, that word is itself composed of letters, and a for loop can help you access each one in order. Now, the way that that's going to work in today's code is that we're going to be using the arguments that were passed by the user to our script, and by doing that, we're going to have this list of strings that we need to deal with. And so each arg in sys.argv will be a different argument that was passed to our software. So lists can show up in lots of places. They don't always consist of lists of numbers or an index that's running from 1 to 10 or whatever. That is not the only way that people use looping, though. Very frequently, you're not sure how many times you're going to have to execute a piece of code. And if that's true, you probably have some sort of logical condition that specifies how many times the thing is to take place. It won't know from the beginning, but it can check to see if a certain outcome has been accomplished, and if it has, it can stop, and if it hasn't, it'll continue looping. That's what a while loop is for. Now in this case, we're using another import. You can see that we're importing the module random up at the top. I think a lot of people know that when you compute a t-test, you get a p-value, right? People have used t-test presumably at some point in their academic training. So if you run a t-test, you're going to pop out some p-value. Now if there's no difference between the two cohorts you're comparing, the p-value that results is randomly distributed, uniformly distributed in this case, between 0 and 1. So you're comparing two sets of numbers, 5 values here, 5 values there, whatever it is, and you compute a t-test, out pops a p-value. If there's no difference, you can get a very low p-value, or you may get a very high p-value. You don't know. It's uniformly distributed. So we're going to model that behavior here. We're going to see how many times we have to do a random number in order to get 5 hits, p-values below 0.05, right? We see that all the time in science. People say, if I run a t-test and I get a p-value below 0.05, these two distributions are not distributed not distributed the same way. They don't have the same mean. Okay, so in this case, we're going to count how many hits we have so far until we have 5 random values that fall below 0.05. So how do we do that? That sounds kind of complex, doesn't it? But it's not a huge amount of code. Now, we're not actually computing the t statistic and p-values here. I'm just generating random numbers, but the principle holds. So I'm going to count how many hits I have so far. I'm going to do what's called initializing that variable. Count of hits equals 0. And the count of tries is going to reflect how many times we've gone through this loop. And it, too, will start at 0. So while I have fewer than 5 hits, remember we can compare two values through a less than or greater than or double equals operator to turn this into a Boolean situation. So long as count of hits is less than 5, we will repeat this section of code. So we've got our colon here, which means that the next line needs to be indented because it's executed only within this loop. We're going to increase count of tries. Now you'll note I've used kind of a weird assignment here. Count of tries plus equals 1. Have you seen an example like that? Let's take a look at how that would play out here. So let's say C equals 5. Everyone good with that? C's value is currently 5. All right. Now, what happens if I say C plus 5? What's the result that comes back? Someone said 10? Yeah, 10 comes back. But what is the current value of C now that I've run that C plus 5? I hear 10. Still 5. All right, so the value of C is currently 5. It's still 5 because we haven't changed the value assigned to C. Here we used it in an expression that gave us 10, but the value of C itself was unchanged by using it in that expression. However, what what happens if we say C equals C plus 5? It changes now to 10, exactly. So a lot of code ends up relying on a counter increasing by 1. And this is actually part of the reason why we call the language C++ C++. Because the people who were writing C++ wanted to show that their language was one better than C. So the way in C that you increase the value of C by 1 is to say C++. That's not how it's done in Python, though. In Python, you would say C plus equals 1. So every time I run C plus equals 1, the value of C increases by 1. Okay, so this is you'll frequently see this called increment a counter, but that's all it means. We're adding 1 to that value. Okay, so every time we go through this loop right here, this count of tries is going to be incremented by 1. We're then going to compute a random number. The way that we do that is to run the random function from the random module. So random, as I said at the bottom here, ranges from 0 to 1. It's not a normally distributed, it's uniformly distributed. So imagine you had a million-sided die and rolled it. That's going to give you an equal chance of any one face showing up. In the same way, we have a uniform distribution from 0 to 1 in random. Okay, so if this random value is less than 0.05, increment count of hits, and print what that random value is. All right, now this next line is no longer indented. It's all the way back at the beginning. So what does that tell us about which parts of this code repeat every time the while loop executes? The first part that gets repeated is count of tries. The last part that gets executed is to print this random, but only under the circumstances that this if condition is met. All right, so let's look at the code for that. I've got this example down at the bottom of the code that you used today. Oh, and it's a little off screen here. Let me change the screen. Okay. There. So I'm going to just run this code right as it is. Oh, I have an error in my code. How embarrassing. What did I do? I think this is one of those things where my indentation gets changed when I try to copy it as opposed to when I do it. Okay. Oh, I didn't run the import. That's what happened. Sorry. Import random. Much better. Okay, let me try repasting that. All right, and then the last line was we generated blah 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 tries. Okay. So the software has dutifully outputted 5 values. What are these 5 values? First off, did you get the same values on your computer? You should not. Your computer and my computer are generating independent sets of random numbers based on whatever random number seed your machine is operating on, mine is operating on. So in my case, my numbers are my numbers and they're not going to look exactly the same. But what should be true of your numbers and my numbers is that all of these should be below 0.05. And why is that? Because this print statement down here only happens if the random value that we started with is less than 0.05. Okay, so number 1, number 2, number 3, number 4, number 5, these are the 5 values that met this below 0.05 criterion. And then this last print function reports how many tries it took in order to get those values. So my computer had to generate 54 random numbers before it was able to produce 5 that were below 0.05. One way to read that is that my machine had run 54 t-tests in values where there were no differences between the means, and it still found a difference between the means. That the means were not the same. So if you ran something like that on your machine, did you get the same number of numbers? Didn't. 100 and 123. Oof. Okay, so a fair number. All right. I'm gonna run this a few times on this machine, and we can just see how many times this goes. I'm sorry, it really hates that last line, so I'm going to. I think I need to add a white space in here. There we go. Maybe that'll behave itself a little better. I'm sorry, sometimes code behaves a little differently if you run it in interactive mode like this, rather than running it in as a script separately. Okay, so in this case, the number was actually perfect. And why would I say it's perfect? What's the chance randomly that a number chosen uniformly distributed between 0 and 1 will be less than 0.5, let's say? If you have a random number between 0 and 1, what's the probability it's less than 0.5? 50%, very good. Okay, so in this case, we've got a more stringent criterion than that. We're saying the number has to be less than 0.05. So what's the probability that a random number between 0 and 1 is less than 0.05? It's 5%. It's 5% because the interval from 0 to 1 is 20 times larger than the range from 0 to 0.05. Okay, so in this case, if you generate 100 numbers, that's the number you would expect to produce in order to get 5 random numbers below 0.05. And if I repeat this code, 186, that time it took almost twice as long to get this number of numbers. 159, 160, 85, it's different every time. Okay, well, so we see then that we can run this code and get a case where the software decides how long to keep iterating this code based on whether its condition is met or not. Is it possible that this code would never finish, that that loop would be infinite? I bet you I can make this a code that won't finish. How about I say, if this random number is greater than 1, you see that? Now, under how frequently is it going to rack up hits? I just changed the rules, right? I said when it generates a random number, it should only count it as a hit if it's larger than 1. But what does random return? Random will only return numbers between 0 and 1. So I can start this code, but it will not finish. We can wait all day. It's not going to finish, so I can Control-C out of that. So you can see that in that time, the computer generated 16 million random numbers, none of which generated a hit. Okay, so it is certainly possible to write code that can't complete, and that's always a little embarrassing. Let me see, I think that originally said below 0.05. There we go. Okay, so I believe, yeah, that was the last topic I wanted to just rattle on about, but along the way, we got to work through some of the code examples. Now, all of those are in this sets iteration Python code. I also included the code examples from last week's stuff, so you can work through those again if you like, the string finders and so on, and the conditional code is in there as well. So I would like us to look at a different piece of code now, and that would be a look at goal 2. So we wanted to change some things about the code. Last week, we provided the name of the FASTA sequence database in a hard-coded form. Does everyone remember that? We can look back at it if you'd like. Oops, sorry about that. I'm going to drag this down here and open up goal 1. This is last week's code. So you can remember last week's code said this FASTA equals, and then it gave that string in hard-coded form. So that was fine, but remember that if you release this software to other people and they don't want to use it on the Mycobacterium tuberculosis proteome, but rather a completely different protein sequence database, it's of very little value to them. They would have to know enough Python to go digging around in the script in order to change the file name. That's really kludgy. So instead, we want to be able to have users choose the file name for their for Python to sniff on the command line. So let's imagine I've just opened this command prompt. I need to get to to the location where my files are located. As you can remember, I set them up in a UWC Python directory right off of root, just to make it easy to get to. So I'm going to type cd/UWC Python. I can take my directory and see that I'm there. Okay, so we're going to be changing things a little bit now. Instead of just running the script as is, I need to provide information to the script. So for that, we remember that last week we set Python on the path, which makes it easier to call the software. One of the reasons we needed to do that last week is that we're going to be using that for the rest of this time. So if your machine doesn't have Python on path, let me help you get that corrected before we leave today, and we'll make sure that we get that nailed down. But I'm now going to launch the script for today, which is called 2019-0718 goal2.py. Okay, if I run it just like that, I can see that I get an error message now. The software says no FASTA provided, exiting. And, importantly, when the user didn't provide us enough information, we tell them what information we were looking for. So you can see that our usage line says that you should give, the software will give statistics for the FASTA provided on the command line. Sorry, the screen is a little wider than what I can show. So when I run it, I should say Python FASTA Sniffer.py, which is our eventual name. The software is currently named this Goal2 business, but eventually it'll be called FASTA Sniffer.py. And then I'm supposed to provide a file name .fasta right there after it. So I'm going to hit the up arrow to repeat the last command I ran. And I'm going to enter some nonsense here. Nonsense. When I hit enter, I get the same error. You see that? No FASTA was provided. I can also, but I can say, oh, I actually meant to say nonsense.fasta. You can see now it has interpreted that differently. I don't get the no FASTA provided. It now says, this is the FASTA we will use, nonsense.fasta. So what changed between these two? The difference was that I added .fasta to the file name. So from a programmatic perspective, how does the software go about interpreting what came back? All right. So it starts by saying this FASTA is an empty string. We're going to create a variable to store the FASTA file name, but it's going to start with an empty value. Remember that by importing system, we were able to get arguments that were made available to the software. So we can then loop through each of the arguments that was passed to the software, and for each one we can ask, does it have the string .fa within it somewhere? So when we look back at these two values, we see that nonsense does not have .fa within the string. Nonsense.fasta does. Somebody might even have said nonsense.faa, which is an amino acid sequence database. That would also be fine. That's the FASTA we will use. Okay. However, I would note that it is possible that someone has provided multiple FASTA names to this. So I'm going to say first.fa, FASTA, let's say, and second.fasta. I'm calling this software this time with two FASTA file names. So we have a little mystery here. The user has done something we didn't anticipate. Have you ever heard the phrase, design your software to be idiot-proof. Have you heard this phrase? Computer scientists jokingly reply that if you make your software idiot-proof, the world will make a better idiot. It's very unfair because our users are ingenious and they're just trying to solve whatever problems they've got. So imagine that you as a user have a whole directory of FASTA sequence databases and you want to characterize them all. So maybe you would do something that would seem sensible to you, like star.fasta. That's a very ordinary thing for a user to try, and yet your software may not be equipped to handle that. The way we're writing the software, it will analyze one FASTA file in one execution of the code. So we have to be careful that we specify to the users, you can only give us one FASTA file name. All right, so having provided it first.fasta and second.fasta on the command line, why is it declared that it wants to run only second.fasta? We can see that it's looping through all the arguments in sys.argv. The first of those is the name of the script itself. So the first argument is going to be 2019-0718 goal2.py. So the software is going to start with that argument and check to see if that's a FASTA string. It's a bit of an ugly thing because it could create a problem if you'd named the script to include .fa as part of its name. But instead, having looped through each of the arguments passed to the software, each time that it finds .fa within the file name, it sets this FASTA to be equal to that. So this is a case in which we provided two different arguments that both met the criterion, and it overwrote this FASTA each time. So the first time, when it encountered first.fasta, it said, that's a legitimate name, I'll use that. But it wasn't done iterating through all of those possibilities. What happens if instead of saying second.fasta here, we say first.fasta and then second nothing? You see, it is detecting that first.fasta is a legitimate database name. Legitimate here being that it contains .fa. When it sees second, it does not accept it as a FASTA file name because it doesn't contain .fa. It's only this case where both of them contain FASTA that second.fasta overwrites the value of the first one. So keep in mind that software can do lots of squirrely things, and it's okay to print lots of debugging messages along the way. We could, for example, have it report each argument as it sees it. All right, so if I've now changed my script, here I'm going to rerun the code, and you can see that first it prints 2019-0718 goal2.py. That's the name of the script itself. Then it prints first.fasta, then it prints second.fasta. I might add even another print statement in here. Sometimes my print statements are very enthusiastic. All right, so I'm going to rerun. So it's still printing each of the arguments in succession, and it's going to give us a "we got one" message every time it satisfies the if. We got one, we got one. And I have to say, before debuggers came along, this is how an awful lot of people found the bugs in their code, adding lots of print statements and trying to figure out why it was triggering this or that condition. All right, I'm going to go ahead and strip those out of there again. All right. So we can see that on the command line, it's always going to take the last one that contains .fa. Now, we next have a condition that we're setting here. I think people remember from our in conditional execution last week that we talked about how it responds in response to various conditions. So here we say, if this FASTA's length is less than 1, which is to say, if there's basically an empty string to represent the database name, then it's going to say no FASTA provided. And it's going to run the quit function in order to kill further execution. But if it doesn't run that condition, you can say the user did specify a sequence database. Now let's check one other thing here. This is something that may come as obvious to everyone, or it may not. You can see that the software seems very content here. This is the FASTA we will use, first.fasta. But does that mean that first.fasta exists? It does not. At this point in the code, we have not checked the file system to see whether or not that file actually exists. So it is possible that the user has provided us a FASTA database that doesn't exist. It's possible that the user has provided you a FASTA file that is not accessible to this user. You know, maybe it's over in the root directory or something like that. It's possible that the person has given you a FASTA file name that does exist, but it's misformatted. Maybe somebody tried to write a FASTA file database in Microsoft Word or something. There are lots of ways that file access can go really squirrely on us. But that stuff is going to come next week, because next week we're going to learn how to read a text file off of the disk and begin actually sniffing through these FASTA files. But for this week, we're just discussing this concept of iteration, the for loop in this case, and how to get input from the user on the command line. So that's now in place. Okay, so next week we'll be back in here at 9 o'clock on Thursday morning, and we'll be dealing with file access, which has a few peculiarities to it, so I hope you'll be able to attend. This lecture and the others will all appear on my YouTube channel as we move along. Thank you.